Right. So, today has been a kind of a data structure day, and let us do some more data structure. Data structure is interesting, it is helpful. So, we now know to search for a point in logarithmic time within a subdivision, and that is kind of very essential, because otherwise n to log n is a kind of an exponential fall, it is helpful. Okay. So, I would sort of continue from where Orithro left. Orithro did for you. So, it was right, it was range query, and what Orithro covered was KD tree. So, what you essentially have is a set of points in some dimension, which you sort of pre-process. You pre-process the set of points, and such that, so pre-process P such that one can report the points P I belonging to capital P that lies inside the query rectangle Q. So, given a query rectangle Q, and you are asked to sort of report all the points that lie inside. Now, there are interesting versions of this query where you can move from a rectangular region to, say, you give a triangle and ask for the points inside, you might even give spheres and ask for what are the points inside. So, there can be different kinds of, these are kind of called range queries. So, there can be different kinds of range queries. Rectangular range query is the simplest thing that you learn first. Okay. And what Orithro dealt with this problem only in dimension 2, right. Okay. So, and I think the query complexity that you learnt was square root n plus k, right. So, what you can think of is, so this was like reporting query, right. You had to report the points that lies inside this query rectangle Q. I could have asked you a small different variant of this, where instead of, so this was kind of this reporting query, you had to report all the points that lied within the rectangle Q. There can be a different version of it, where I am just interested in the number of points inside Q. I just do not want their explicit coordinates. In the input you give me a Q, I have to report what are the points, number of points inside. So, these queries are very mobile region, tower region, you have mobile towers moving. So, you give a query and you want to ask how many users are within a particular range. So, this kind of, so if you are doing a reporting and counting, so you can be a little bit intelligent to get rid of this factor in your counting, and you can have something like this. So, think of this over. In tutorial, maybe Shushovan and Ananya would sort of give you some idea about how you can do this. One can think of even extending this to higher dimensions, where I think the complexity is, if I am correct, something like this plus k, right. You place d equals to 2, it is half, no. So, if your points are in d dimensions, think of building a structure like this. So, again there the structure is like the first you take the discriminant x value, the median of x splits into 2, this half you sort of split on the median of whatever points are y, right. So, there it was like x y x y x y, no. Here it is like if you are in 3, x y z x y z x y z. So, if you are in d dimensions x 1 x 2 x d, again x 1 x 2 x d. So, this is the way you partition. and then because of that particular kind of recurrence logic that you had to write a correct recurrence. So, you had to go down by one level. So, here you have to go down more levels, no, d levels, there you have to go down 2 levels to write a correct recursion. Remember, that is what Orithro was doing for you. So, kind of writing a recurrence like was something like this he wrote, no, plus, right. So, here actually then you have to take care that you shift by a thing of like d and do the stuff. So, you can write a recurrence for higher dimensions and then that would solve to this. So, let us not get into too much there, but what as so I mean the way many of us in theoretical computer science see computer science is mathematicians are happy with existential proofs. For computer science you always try to get constructive proofs, and an algorithm is nothing but a constructive proof. So, essentially your idea is to always do something better, try even more, try to be more efficient in terms of data structure size, efficient in terms of time complexity. So, there can be different notions of efficiency and you want to be as efficient as possible. So, in this problem let us think of the same setting, and this is like square root n, right, subquadratic. So, it is square root n, it is like not very good, n to square root n, okay. Then can we do better? That is the question. Okay. So, sub square root, that is what we want, something less than square root n. So, n square root n, then what is your favorite function of n? Log n. Okay. Let us see if you can go there, but to go to log n probably we cross this, no. So, we try something like this and then possibly we see if we can do, that is the agenda for this lecture. Now, this is what your KD tree is. So, we will talk of another data structure known as range tree, and then finally, we will give you some idea about a data structure which is known as fractional cascading, kind of it is a layered range tree. We will see what I mean. So, this is the idea, fine. Now, see the basic idea So, the basic idea that of any data structure that supports range queries is as follows. What Orithro must have done is, it talked of a root, right. The root corresponds to all points, then he splits into 2 halves by probably the median x coordinate, no, into 2 halves, and then again he splits this into 2 halves, this into 2 halves, keeps doing, ensures that the split is balanced, that is why you take median and you keep going, no. Now, notice, so here was the big chunk of points within a big rectangle. So, your root as it contains is sort of equivalent to all points. I would say that the root corresponds to this full region. Okay. Now, say so you had taken the x median line, no. So, that means it had split this rectangle somewhere. Now, if in your search you have gone left, it meant that look in this region, fine. Similarly, in here if you have gone there, then again here you had split with, here the splitting was with an x line, here the splittings are with a y line, fine, horizontal line. So, then if you are going right, then that means up, no. So, that means as you keep following a path in this tree, you are sort of slowly squeezing a rectangular zone to reach to a particular location. That is what your search on this data structure is. And what you have been given is a query rectangle, right. If it so happens at some point this region that you had obtained by going along this fits snugly inside this query rectangle, then you know that all points inside that small rectangle which is encompassed by this query rectangle, all points inside should be reported. Else what you do is intersect your query rectangle with the rectangle obtained here, and in that sub part do your recursive searching, right. This is the basic idea of any data structure that supports range queries. So, as you make a root to leaf path, you are essentially working on nested rectangles, fine. So, this was your first rectangle, the big one. Your next rectangle was this one, your next rectangle was this one, then again possibly you went this side, then possibly it was this one, so on and so forth, no. So, any search is basically getting into nested and nested levels of rectangles, and based on this, so any node in this tree corresponds to a rectangle. Now, based on the relation of your query rectangle with this rectangle, you do a following things, that if your small rectangular region obtained from the traversal on this tree is fits inside a query rectangle, then you are sure that all points within the small rectangle will lie within your query rectangle. If it intersects, take the intersection region and do a recursive search on that. Change your query rectangle to this new intersection, right. So, if it so happens, say for example, your query rectangle was this. Okay. So, in this part, in the left part of the tree, you obviously go with this rectangle, and in the right part of the tree you go with this rectangle. So, what you do is, so you intersect your query rectangle with the rectangle determined by the particular node of that tree, and with that newly obtained query rectangle continue the recursive search. This is the philosophy of any range search. Now, how you do this intelligently or how you do this more efficiently would give you a better search time. Okay. Now, our goal is to come up to, as I said, this. So, to do this, let us first, did Orithro talk of a 1D range search, right? How much time did it take? Log n, no? Log n plus k. Okay. So, the k is that reporting thing, forget about that k. So, it is log n. Essentially what he was doing. So, let us just, to be on the same page, let us just look at it. Here is your, this is your 1D range tree. This is your think of your AVL tree or balanced binary search tree on the x coordinates, fine. What you are given is a range like x x dashed. So, you keep searching. Now, 1D range tree is basically, it orders the points on the real line, no. So, this x x dashed is somewhere. So, what you do is first search x to x dashed on this. If you see that the value stored in here is less than x, then your search path should go right. If the value stored here is more, then the search path should go left, right. Okay. So, that means your search path keeps finding a node such that the value present at the node lies in the middle of this range. Till that point, it either goes left or keeps going right, fine. Okay. So, let your path be something like this till you obtain a node which has a value that is within this interval x to x bar. So, let us call this node to be the split node. So, on this split node, so there is a value stored here, let that be some x 1. So, after the split node, I would keep searching in, from here I have to give searching in both directions. No? On the left I should search with x 1, on the right I should search with x 1 x dash, agreed. Okay. And so, this search path would sort of evolve like this, to finish somewhere. Now, see, if you consider any node in this search path and consider and say this fact has happened, that after this comparison in this node, your search path has gone to the left. Okay. Then what can I say about the values stored in this subtree? They are completely inside the range x 1, because they are greater than x 1, small than x. So, the moment after the split node, if ever your search path on the left half goes left, then you can safely report the right subtree, and similarly by by an almost similar logic, if it goes here, you can report the left subtree. Our book gives this kind of things a good name, let us call them to be canonical subsets. Maybe Orithro has even given that name. So, there will be many such canonical subsets, no? For each node there will be some, no? There will be many such, no? How many? Huh? K many? Per level there can be how many? Hey, come on, there can be at most 2, no? Because extreme left it is going right, extreme right it is going left. So, there can be in all. So, this operates on the depth, no? So, think of this path, this is kind of a logarithmic path, and at each level on this path there can be at most 1, no? And similarly here, so 2 log n kind of thing. So, there can be such log n many canonical subsets, and in each one of these canonical subsets you can safely report that this point is within the search interval. So, this is kind of looking back at searching, interval searching within a balanced binary search tree. I will just try to take this idea over to 2 dimensions. If you have understood this, range tree next is not much difficult. Now, see, when I have come to a, when I am reporting a canonical subtree, what I am sure of? I am sure that their x coordinates all lie within the range within which I am querying. No? What is a 2-dimensional query? A 2-dimensional query is something like this. So, what it tells you is, if I can do it this way, that here is my set of points, I first figure out by a binary search what are the points in this slab. No? This is like 1D, I pick out all those points, arrange a balanced binary search tree on their y coordinates, and then on that, only on those y coordinates I kind of do again a binary search. Then I can figure out the points inside, right. One binary search, I pick up all x coordinates, forget about the rest, take them, then again form a balanced binary search tree on them, then again do a y bar kind of interval search on this slab only. Then I can correctly figure out the points inside the query rectangle. Agreed? But if I do it this foolishly, then I will be obviously taking much more time, because it might so happen that once you do this search in this x to x bar, almost order n many points may come. No, most of the points come here. Then again, if I am to build a search structure on that, I would again take n log n time, then search. It is kind of a mess. But what I will do is, I will do this a little bit intelligently. So, when do I mean in this foolish way in which I narrated to you this thing, when did I do a search on y? I did a search on y only when I was sure that I have correctly located the x slab. Go back there. When exactly have you noticed the correct slab? When your x, so in here when your x bar has on the left part after this split node is going to report a bunch of a subtree of which you are sure that this x's surely lie within x to x bar. Now, if you look a little bit intently and look at the x intervals induced by each one of these trees, they are nothing but some partition of agreed. So, if I look at the leftmost, so look at any canonical subtree, look at its leftmost value and rightmost value, they are an x interval, right, and that for this surely lies within x bar. You are with me? So, essentially a left to right walk on the leaves of this canonical subtree gives you a walk on this partition from left to right, and these are nothing but your slabs, slabs within which I am sure of the x values. So, say for example, when I am here, so for any value in this subtree, I know that its value maybe is lying within this interval only, right. Now, mind you, at the very beginning I said that each node in a range tree sort of points to a subset of points. The root points to the whole set, this points to some PL, these points to PR, and mind you PL and PR are disjoint. So, that means each node in your range search tree, KD tree, range tree, whatever, corresponds to a set of nodes. Fine. Now, come back to your 2D range tree. So, my first goal is, what I do is, I look at the x coordinate of all the points, construct a one dimensional range tree over the x coordinates only, right. If I do a x bar kind of search on this tree, I will correctly locate all points that satisfy the x coordinates. I am not sure of the y. So, in that what I would do is, whenever I am in a node anywhere in this tree, I know the set of points it corresponds to, right. What I will do is, I will associate another structure, another tree with each one of these nodes, which is built on the only on the y coordinates of those points that are associated with those. Fine. So, think of this tree, a balanced binary search tree, kind of a 1D range tree on all x coordinates. Fine, easy for you, you very well appreciate this. Take the root. The root corresponds to all points. Build a one dimensional range tree on the y coordinates only for all the points at the root. So, this is like in all points, come to its left, come to its, go to its left, go to its right. Left corresponds to half of these points. No? For these points, again build a range tree, 1D range tree on the y coordinates of this half of these points, again here, right. Keep doing this. Okay. Now, there is a problem, because you are building in a redundancy, building in redundancy. Okay. So, that means space wise I might be a bit bad as compared to KD tree, because a point I am going to store multiple times. No? Think of a point here, right. It will appear once for this root, at the next level again it will appear either for this or for this. No? Again at this level that point would occur, any one of these 4, no? It is not more than one per level. So, any point is going to be stored once per level. How many levels are there? Log n. So, your space can go up to n log n. So, you understand the space analysis, right. Okay. So, your data structure now looks like this. It is kind of, you can think of this in your head, this managing this pointer business. So, think of any path. So, you are storing this tree, then for this you are storing another tree, but this is of half size, again this is of half size, keep doing, and here also the. So, in the leaf store the exact coordinates, fine. So, again there is another and so on and so forth. So, this point gets stored here, 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 but we have argued that per level a point is stored once exactly. I mean, why should I even write at most, is stored once. So, your space blows up to order n log n. Search. What about search? Till split node I do nothing, right, I keep searching. but in here whenever in the 1D search I was sure of a canonical subset that I could report, there what I do is for the points corresponding to this there is an associated structure on those points, there I do a Y search, because that associated structure is built on Y, right. So, how many such calls can be there to the associated structures? As many as canonical subsets can there be. How many of them are there? No, log n, no, order log n, right. Your number of canonical subsets can be log n. So, whenever you encounter a canonical subset and in your 1D range search you are reporting a range, there instead of reporting now a range, go to that associated structure, initiate a Y search there, right. So, now let us do the query complexity timing. So, each search in the associated structures can take log n plus some like this, right, and there can be how many such searches? As many as your associated these canonical structures. How many of them are there? There are log n many, no. So, this is done. So, your space is sorry what I am doing, space is n log n, no, that is what we argued, yes, space is n log n and your query time is log square per n. So, your exercise is Ananya, can you just check if I did put this exercise here, that generalize this to higher dimensions? Oh, you do not have the printouts of the tutorials, no, with you? Printouts of the tutorials you do not? Third, this is not there, no? Okay, so I give this here. So, generalize this to RD. So, the same argument works, no. So, here there will be a quantity of D. So, it would be kind of log to the power of D minus 1 by n, and this would be kind of D kind of such. So, you have to develop a recurrence, right, to solve this, no? Generalize this to is. So, the way you do it is use a recurrence. So, play on the dimensions. Now, our goal was we have reached some height, but we want to even go above. So, this is our next goal. What is your idea? I will probably spoil your this new page adder or whatever. It never works for me. Oh, top, there is a top thing. Where should I get it? Insert. Insert. Oh, insert new page. Yes. Why do you give multiple options then? Huh? Windows. So, just once read what Richard Stallman tells about Windows. Anyway, yes. So, my goal is to get from this to this. How do I do? Notice a fact that how did I obtain this log square n plus k? I did a summation over log n terms where I had an inside log n plus some this, no. So, if I am to obtain a log n plus k by this kind of thing, then I should look at what? This should be order 1, no? Otherwise, there is no hope. So, I am asking you to do a Y search in order 1 and then do log n many kind of these things. Then I can, right. My algebra tells me that it can work this way. How can I do this? How can I explore, possibly exploit the storage in the range tree to get kind of this order 1 plus kV? Hash, hash is very difficult. I do not know hashing. Hash is, you do not hash anywhere, no. Hash is reserved for certain purposes. It is like with an LMG you do not fire at mosquitoes, no. You need these Chinese bats. Okay. So, you should be careful of the weapon that you are using, no. Just go back and read where you exactly need hashing. You have to argue on the universe size, then it is like it's never use hashing anywhere until and unless you are very sure. Okay. There are many people who possibly do not know hashing, so let us not get into hashing. You have any other idea than hashing? So, take it that I do not know hashing, so just I cannot do anything with hashing. So, let us do it this way. Any other idea other than hashing? Oh, you saw this big O of 1 and then you suddenly it is hashing, no?
Because sir, hashing uses constant time.
No, hashing uses constant time after many things has happened. It is just not out of the blue that it is big O of 1. There were many things on the assumptions on the input and then and only then this did happen. Anyway, let us forget it. Yes. Can we exploit some properties of this data structure? Yes. See, the point is, see, this redundancy did help me, no? If you are going to remove this redundancy, this would affect the time. This redundancy actually helped me in getting to log square n from square root n. Okay. Think of this search path going. Okay. Now, the crucial idea, and if you just understand this idea, then fractional cascading is not very difficult. It's I mean, if I teach you it in the formal way, there would be enough pointers going here and there. It's kind of messy, but if you understand the philosophy, then it's like very easy to see. Now, look here into this crucial observation. that whenever you are searching with a y thing for, you look at any associated structure at any level, okay, and look at its associated structures at, look at, oh, this is a no go zone for me, no, I cannot go there, okay, I have to be here only. So, look at any node here, fine, this has an associated structure. Look at any node in this subtree. When you look at the associated structure corresponding to this, it is a subset of its parent. Right? We argued on this, but the philosophy of any range search tree is nodes correspond to bunch of set of points. So, if I look at any node in the subtree rooted at this node, then the associated structures that correspond to this would be subset of its parent, right. So, as I keep falling, I am sort of getting to smaller and smaller and smaller subsets, right. Let us now look at how I handle such goings. Say for example, I have two sets of numbers. Now, just forget about range tree, fractional cascading, so forget about everything. So, I have two sets of sorted numbers. Oh, this is vector graphics, I see. Maybe I will have something more 111. Okay. I now look at another set which is a subset of this, and I have 10, 19, 32, 62, 70, 80, say 100, and say even say 105. Okay. And my goal is to search in both these lists. These are sorted lists, both these lists. The only thing that has happened is S2 is a subset of S1, and I am to search with say a range. Let us even look at this value here, range 20 to 65. Okay, that is what our book says. So, what I can do is I can do two independent searches in S1 and S2. Fine. But if I do a little, if I am a little bit intelligent, I know that if I have correctly figured out some values to be lying within this range S1, then I can manage S2 also in a nice way. So, what I will try to do is, see what happens for a binary search on S1. You keep on shifting to get a split node, and then you go left, then you go right. What are the values in the list S2 of which I would be sure to lie in an interval with which I search S 1. Say for example, I have hit at a node, hit at a value here, then any value that is greater than equal to 23 qualifies to be in that range. If it is less than 65, well and good. If it is not, then I will throw it out. So, independently I can do 2 log n searches, no. But my goal is, if I can pre-process these 2 arrays in some nice way such that I will never need to search in the next S 2, there it would just be a walking. Mind you, my problem was report in S 1 and S 2 numbers in here. Okay. Now, what I do is, for each member in S 1, I keep a pointer to some value in S 2, and what should be that value? It cannot be same, no, because some members of S 1 might not be present in S 2. The least number greater than this number. Right? The least number in S 2 that is greater than. So, for a number here, I will look into a number here, the lowest number that is greater than equal to this number, no. So, just arrange your pointers correctly. So, 3 goes to 10, 10 goes to 10, 19 goes to 19, 23 goes to 30, 30 goes to 30, 37 goes to 62, 59 goes to 62, 62 goes to 62, 70 goes to 70, 80 goes to 80. The last part I had just missed up, this was not a good example. And no, as this has nothing to go to, just make it a null pointer, point it to null. Okay. It is similar to, no, this is not skip list exactly. Skip list, well, you might say, but skip list has a probabilistic thing to it. Yeah, you might say, but skip list has some lift, right. No, let's forget about skip list. Okay. Okay. Now think of a search with this range 20 to 65. What will happen? So, what you have done is you have stored a 1D range tree over this set of numbers S 1, no. Then you will do a binary search, get a split node and hit 23. The moment you hit 23, you know there is a pointer to, and this part of S 2 is I do not need to look at, right. So, in a logarithmic time, I have been able to, this log n plus k time, I have been able to figure out that these are the numbers, right. So, now whenever I come here, it is just about walking on this list, no searches on this list. The search is only on the top list, fine, no searches on the bottom list. On the bottom list, it is a pointer that leads you there, then you just keep walking till you report get 65, fine. So, in here you report this, no. So, earlier it was a log n plus k and a log n plus k, right, k 1 k 2. So, earlier it was a log n here plus a k 1 and here also it was a log n plus k 1, no. So, maybe let us make it k 2. So, it was 2 log n plus k 2, now it is. So, I have saved one log n. Now, you can even extend this by considering an S 3, S 4 and you manipulate your pointers in the exactly in the same fashion, right. The only thing is S 1 is a superset of S 2, S 2 is a superset of S 3, S 4 is a superset of S 2 is a subset of S 1, S 3 is a subset of S 2, S 4 is a. So, the only thing that I require is this nested subset relations. Then in so only logarithmic search is in the first level. In the next level there is no search, just a walk, fine. Okay. Now, I go back. Think a range tree. I have these subset relations among all of them, no. This is a superset of both of this. So, what you now do is instead of a tree there, keep an array. Earlier it was a balanced binary search tree on the y coordinates, now make it a array sorted on the y coordinates, fine. Here also make it an array sorted on the half of these points, y coordinates of half of these points, and then you manipulate pointers in that way to both these structures, fine. So, see how many extra pointers are you adding per array position of S 1 1, right. So, whatever the storage is, you are at most doubling it, no, asymptotically it does not grow. So, from per array location one pointer is coming out. So, whatever is the bigger size, that is your number of arrays, that is the number of pointers. So, asymptotically the space is not growing, it is T in L log n, but search, how is now the search going to work? Mind you, my philosophy was to get this, okay, but we were almost home. I mean, so the essential idea is now in the associated structure stores those arrays and just manipulate the pointers, right. So, each one array is a subset of the previous one. So, now there are some pointers going to the left arrays, some pointers going to the right arrays, and this arrays keep on sort of percolating. So, that means when you are initiating your search, whenever now your search sort of, how does your search progress? It progresses level by level, right. Whenever you are going to an associated thing, mind you, what was your range tree kind of search? That whenever in this search tree you are going left on the left of the split node and you are reporting the right subtree, then you are initiating a query on the associated structure here. Instead of that, do a associated thing on the array stored corresponding it, and then again keep going using those pointers to its next levels. So, you need a log n at the very beginning to get to the correct position of the first array, and then it is kind of uses these pointers to go across to different levels and keep walking on that level, right. That is for you to work out. Drawing a simple example with this is, how many pointers have I to draw? Do you have any estimation? N log n, I mean, if I take say 6 numbers, how many? Maybe I have to draw at least what? It's 3, no? So, 18 pointers and then think of levels, 18 into 3 54 pointers. I am not going to do it for you. You should get, you should start learning things abstractly, right. So, you go back and you go back in your home, take an example. I have given you one example. No? The moment I have this, even I can show the example on the book. It has not drawn all the pointers, and it will kind of a so messy a drawing, because pointers would sort of cross. No, it is like it will get very messy. So, the essential idea is level by level you go, but when you jump levels, now there is no logarithmic search. You are just walking on levels. So, our essential idea was per level I do this kind of thing, and you are doing a logarithmic search. No? So, if you have understood range trees and if you have understood this argument, we are really home. Earlier it was always an independent search on the associated trees, but we just use this observation that the associated structures are nothing but subsets of its parents, and then I just invoke this argument, and then this in order 1 plus kV follows. So, this is kind of a great improvement, right. There was no jump in space, right. I just grown by a size of 2, at most 2 maybe. I was just using some pointers extra. The rest is nice, no.
So for d dimensions, how can we like
So, you would get kind of, that was log square n. Okay. So, that was log d n. Here you are looking at, so range tree was log d n. So, fractional cascading would be, it is a shaving off by 1 log factor. Okay. So, essentially you have to write a recurrence like the one I asked you to do for range tree, do here accordingly, and use the base case. No? For the base case you know how to handle. So, take the 2 dimensional case as your base case, then you know it is log n plus k, and then you have the base case and you form the induction, the recurrence, you are done. Any queries? Okay. So, we have covered a lot of ground. We know how to locate a point in logarithmic time in a trapezoidal decomposition or in any planar decomposition, and we have also now know how to handle geometric data structures. So, we have sort of, log n is kind of a good search, and we have been able to figure out a range search in log n.